One thing over here. Notice. Different order of operations, okay? So I'm just going to make a list. You do not necessarily have to do this part, okay? So I'm going to abbreviate diff order of ops, not opera of ords. Order of ops. Okay. So anything else that you wonder? You said you had something you wondered.
I was just going to say that they all have the 7 and the 9.
Okay. So are you wondering why they have, or do you know?
No, that was just something I noticed.
Okay. So different order of ops, but all have 7. 7 and 9. Okay. Anything else in the order of noticing or wondering? Let's go from way over here. Quant's table. What you guys come up with? Anything different? Nope. Rudy, how about you guys? No? Melanie? No? Gage, you guys come up with anything that you noticed or wonder different?
Nope.
Nope. Wow, you guys are awesome. All right, anybody overall come up with anything else besides they have different order of operations and they all have the number 7 and 9?
They all equal to
Caleb.
7 comes first.
Okay, so in all of them, 7 came first in the order. Okay, anything else? Notice or wondering?
I wondered how the answers can be related.
Ooh. How can answers be related? Because there seems to be some sort of pattern there. Okay, anything else?
They all equal to something.
Okay. All equal to something. Like, what do you mean by something? A number. There we go. Okay. You know what? That doesn't always happen, and we will see when that doesn't happen. Logan?
So for the first two, when you take the two numbers and add them together,
Yeah.
you get first one you get 9, and the second one you get 7.
Ooh. That's cool. I didn't even see that. Okay. So the digits. So 6 plus 3.
Oh.
Okay. That's something he noticed, so I'll put it down here. So 6 plus 3 was equal to 9. And we had a 9 here. And what was the other one, Logan?
1 plus 6 equals 7.
1 plus 6 equals 7. So one of our addends was one of our digits. Cool. All right, anything else? All right, so we're going to experiment with some integers. So before we experiment with integers, we need to know what an integer is. We need to know what an odd number and an even number is. I think most of you are good with odds and evens, but the integers maybe not so much. So let's come up with a decent definition over here. It doesn't have to be perfect, but easiest way to describe integers is not so much what they are, but what they are not. Okay, so what can they not have? Not a fraction. So if you did not know that, put that in there somewhere. So integers, no fraction or decimal. So no fraction or decimal. We have negatives. Sure. Okay. So pretty much just no fractions or decimals are your only super big restriction. And it's not just no decimals. It's certain types of decimals. Like if I could simplify it, it turns into an integer, then we wouldn't accept it. But in general, we'll say no fractions or decimals. Okay. So here's what I want you to do with your small groups. So if you're not in a group, go cling on to one. And I want you to answer these 9 questions. So the first 6 are a little easier. Okay. It's just talking about adding and subtracting evens and odds, multiplying evens and odds. Not all of them are true. But if you find one that's true, I want a counterexample. Here's what I mean by a counterexample. One example that shows that the statement is false. If it's true, you leave it alone. But if it's false, I need an example of a counterexample that shows it's false. So try these 9 first, and then if you're ready for more, we'll talk about rational numbers. Okay? So start with these 9. So give it a couple minutes. Until 3. So when you show that something's false, all I want you to do is type the word false, and then one single example will work. Okay, give me a couple odd numbers. And when you're doing this, I want you to think about this. Don't make it the same odd number. And 1 is kind of special So you probably want to stay away from that. Okay. So probably the smallest odd we should start with would be 3. Okay. Keep that in mind. Melanie, give me 2 odd numbers. Okay, so one more time. Let's use the numbers, make them different. So 11 and any other number, Melanie?
3.
21. Okay. So 11 plus 21 is not an odd. That is what, 32? Okay, how about 4? Subtract 2 odds. You get another odd? False. So I'm going to do a little Control A, Control C, Control V option. Okay, and I don't know. Let's change it to minus. And do I get negative 32?
No.
Nope, but I get negative 10. Okay, that's a negative even. All right. All the rest of them are true. Okay, so let's talk about rationals. What is a rational? Anybody find a good definition?
Yeah.
What do you see, Noah?
3 numbers that are readable, like 17, negative 34, so they're not non-decimals or fractions.
Okay, so a rational can be written as a fraction. It used to be heresy a few thousand years ago to say you couldn't write something as a fraction. Heresy means that's bad. No. But Pythagoras figured out that you didn't need to. Okay, so rational can be written as a fraction. But not just any fraction. Okay, so sometimes we have some interesting numbers in fractions. A fraction. The numerator can be any real number. Numerator, any real number. Denominator has one slight, teeny, beeny, tiny, but really important restriction. Okay, so remember, any real number. We're going to stick. Well, actually, I'm sorry. Any integer. I'm sorry. Let's stick with integers. Okay, any integer. But the denominator. What do you think the one itty bitty tiny little restriction is?
Not 0.
No 0. Okay. Why not 0? You can't divide by 0. Okay. This is an important distinction. I want you to notice on the 4 original problems, 3 of them worked out to be integers. But that 4th one, when you divide by 7, by 9, did you get an integer? Nope. So hold on to that thought. We're going to talk a little bit more of that today and tomorrow. Except 0. All right. So I'm going to make this around here. That works. Okay. So, no, let's still make it a little higher. Maybe make it smaller. Make it like 18. There we go. Just so you can see the rest of it. All right. So if you add 2 rationals, you'll always get a rational. If you multiply 2 rationals, you'll get a rational. So of these 3, see if you can take another 3 minutes and determine if any of them are not true or false. Yep. A counterexample where when I add 2 rationals, I do not get another rational. So everybody says true?
Oh, no.
You said no?
2 over 4 plus 2 over 4 is 1.
2 over 4 plus 2 over 4 is 1. Okay, so let's look at that one. Okay. 2 over 4 plus 2 over 4 equals 1. Can I write 1 as a rational number? Yeah. How about 1 over 1? So any integer can be written as a rational. So guess what? This is true. Okay. How about 2? If you multiply 2 rationals, we get another rational. Anybody find a counterexample for that one? Yeah, because that's true too. How about the 3rd one? What's your counterexample? No, because that's so 0.666. So this is good. Okay, so if I take 2 over 3, that is equal to 0.6 repeating. Okay, so I could put a little bar over it. That is still a rational number. So repeating decimals are still rationals. Okay. Anybody else find a different counterexample? Even if it's negative. So if I put a negative out here, that still works. That's still rational. There is 1. So this is false. Anybody come up? There is 1. Think about the definition. Think about the definition. 0 where? In the denominator. Okay, so 3 over 0. So remember, 0, that's a no-no. Okay, remember, any integer except 0. So I can divide into 0, but I can't divide by 0. Okay, so 0 itself is a rational number, but I can't divide it. That is the only exception. All right, so we are going to experiment with polynomials. We're only doing 3 experiments. We're doing addition, we're doing a subtraction, and we're doing a multiplication. And I will give you the choice of polynomials. You can choose any 2 polynomials you like, or you can choose one of the ones I give to you. So it's like, I know it when I look at it. I can know when I see it. There's an old Supreme Court decision about that. Look it up. See if you can figure out what they're talking about. All right. So experimenting with polynomials. So let's actually define what a polynomial is. Okay. So there's actually a pretty good definition right here at Math is Fun. So a polynomial has variables that can be added or subtracted. Look, there's no division, and the exponents can only be non-negative integers. Okay, and we're not going to have an infinite number of terms, so we have a finite number of terms. Okay, so constants are okay. So you notice on one of them, I think it was 14.3. It sounds weird, but that's a polynomial. So a polynomial, you're used to seeing poly means many. So we refer to usually things bigger than trinomials as polynomials. So monomial has 1 term, binomial has 2 terms, trinomial has 3 terms. So it can have variables. It can have variables with exponents. And it can have just plain old numbers, which are constants. Look what it cannot have. Negative exponents, and we can't divide by a variable. That's what a polynomial is. Okay? So given that, again, you're going to add, subtract, and multiply in pairs, and then see if you come up with another polynomial. So give it a few more minutes to try it out. Division just yet. Okay? So I want you to look at this second bullet point. It says, when you think of your answer to your question, you can explain your reasoning using equations, graphs, visuals. Most of you made algebraic expressions, which are awesome. But let's take a look at the graphs. So let's do some what ifs here. Okay. What if, Scott, pick the ones that you did for addition.
X to the 7th.
Okay, so here's x to the 7th. Was that just x to the 7th or anything else with it? Okay, that's it? Just x to the 7th?
Yeah.
Okay, and what was the other one?
X plus 5.
X plus 5. What did you do with these 2?
I added them.
Added them. So here's what they look like individually. Okay, one's a line, and one is this kind of funky curve thing. So that x to the 7th really flattens it out in the middle. But if I add these, I'm not going to change it that much. It just kind of moves my x to the 7th kind of up, and then it's not quite as flat as it was. You can kind of see the polynomial, this curve thing. Most of the time it's going to cross both the x and the y-axis. In fact, I think for polynomials it always does. Okay. Anybody else has something different for, let's give me a subtraction one. Hold on to yours, we last. I know yours works. Denise, what did you do for subtraction?
We put -6 squared.
-6. I don't think it was -6.
-6x squared.
X squared, yeah.
Plus 3, and then minus x squared minus 9.
Okay, so when we subtract, what was the other one?
X squared minus 9.
X squared minus 9. Okay, so this one's a little more funky and a little bit more kind of jumps, and that's because of the exponent of 9. Also notice, what is 3? Let's see, got 3 minus a -9 is 3 plus 9, which is 12, which is, hey, look, So my constant, my number on the end, will be my y-intercept. That's something you might want to write down. Okay, my constant. So if I simplify this and just write it as negative 6x squared, I'm going to put it in standard form. I'm going to put my negative x to the 9th first. And then the only two things I can combine are my 3 and my 9. Hey, look, it looks like the same thing because it is the same thing. So the 12 in this case is my y-intercept. Okay. All right.
You said the constant is what?
The y-intercept. Okay. So notice. Oh, look, there it is. 0, 12. All right, we're going to use Bree's for the multiplication. So start me off, Bree. What do you have?
Negative 6x squared
Okay.
plus 3
So same as what Denise started with.
multiplied by 1.2 x to the power of 8.
Okay, so I'm going to put that in parentheses. Close it, put that in parentheses, and multiply by what?
1.2 x to the power of 8.
Okay, so we're looking at a very large polynomial, and then
Minus 7. Minus x to the 7th power.
minus x to the 7th power. Okay. What happened? Okay, it comes up, and it's got this teeny tiny little bump. So if you zoom in, you can see a relative max right here at negative 0.628, 0.43, and then it almost completely flattens off right up until you get to 0.833, and then drops off. What happens when you multiply it out?
You don't like the result?
Yeah, please. The product, yes.
Negative 7.2 x power
Okay. Catch it go.
plus 6x
Plus
to
6.
the 9th power
The 9th power. Keep going.
plus 3.6x to the 8th power
3.6x to the 8th power.
minus 3x to the 7th power.
Minus 3x to the 7th power. Remember what we talked about yesterday? Watch. First it's blue. Now it's green. So what did we just do here? We confirmed that the answer that Bree came up with is correct because this is blue before we multiply and this is green after we multiply, and the graph didn't change. The Desmos has that ability to do that. And it also shows you. So polynomial doesn't have something that we've seen before. So when I take a look at a graph of a polynomial, and we're going to take a look at these a little bit later, probably in the next section, I'm going to take the same problem here. Right here. Ready? Divide. I'm going to put this in the bottom. Control X. Go down. Paste. Okay. Let's see. That's what happens when you experiment too much. I'll make it a little simpler. I'm going to make it simpler. Let's take nice, simple polynomials. We're going to take, like, I don't know, x divided by x squared. Ooh, let's do minus 1. Okay. Woo! Okay. What does this have that the polynomial did not? What do we call them? We've done it before. Got this vertical line here. So x equals -1. And this other vertical line over here, which was x equals +1. We haven't played with them in a while, but it's really close but doesn't touch them. Starts with an A, ends with a tote. Asymptote, okay. So polynomials don't have asymptotes. Hey, these are fractions. What do you think would be a good name for these? One more time? Rational. These are rational functions. So we're going to talk more about rational functions in a little bit later. But with polynomials, you do not have asymptotes. All right. So let's do a little recouping here. So in summary, if we add, subtract polynomials, we'll get another polynomial. We'll multiply, we get another polynomial. What you're seeing here, this little chart, this is called the box method of multiplication of two polynomials. So they multiplied it. So this row is the x squared times these. And then the bottom row is the 4.5 times those. And then what do you think I need to do? After I do all the multiplications, what do we normally do? One more time, Angelica. Add, but we can only add which ones? Like terms. So my like terms here, and if I take a look, 4.5 minus 2, 2.5. So that's a polynomial. It looks really bizarre. But negative x to the fifth plus 2.5x to the third minus square root. So you can have square roots as coefficients. X squared plus 9x plus 4.5 times 7. So this one, I could get a more a decimal equivalent if I want to look at a little bit more detail, but we're not going to do that today. So that is your summary. So now we're going to do a little cool down. So go back into Schoology. Go back into the folder. Go into cool down. Just to make sure I hit everything in the lesson. Is there anything else? Nope. Yep, we did. So the cool downs are like your tickets out the door. You've done in other classes. So that means they're going to get, yeah, but we're going to do this first one together, so it's not too bad. So here are two expressions. Product means what are we doing with them? We are not adding. We are multiplying. So it is implied that I got a little bitty multiplication symbol right in between there. So what can you put in the boxes to make it a polynomial when we multiply? And what could you put in the boxes to make it not a polynomial? So I'll give you a few minutes to work on this. Go for it. So let's do the ones that make it a polynomial first. I am thinking of a type of number. And this type of number, any of this type of number would work. So think more broadly than negative. So for my first number, 4. What else? 3, 2, 10. How about square root of 9, square root of 7, square root of 4, square root of 15? Any of those. Pretty much any real number works for the first box. Okay? So if you just want to put like a little drawing here, and you could say any real number and give me one example. Okay? So any real number. Okay? So you choose. Okay? You get to choose the number. Anything your heart desires would be okay here. My favorite number is pi. I was married on Pi Day. It was March 14th. And then the next two digits are...
Was that on purpose?
16, yeah. So when I asked Mrs. Trilla to marry me, she said, how we get married on Pi Day? I'm like, oh, I know I picked the right one. So we got married in Vegas on Pi Day. 3, 14, 16. All right. This number, a little bit more restrictions, okay? So what's my restriction here? I can't use any real number, can I?
No.
Can I use negatives?
No.
No. So this one has to be, so look at the restriction we had here. Okay, 0, 1, 2, 3. Okay. So non-negative integers is one way you can put it. Also, you learned a long time ago, there's another name for this group of numbers, this set. It's not the half numbers, it's the whole numbers. So the whole numbers are 0, 1, 2, 3. So no fractions, no decimals. So any whole number would work. Whole number, for example, my favorite whole number is 39. Because my dad kept telling me he was 39 years old even when I was like 50. Exactly. Okay. So, boxes that don't make it a polynomial. So this, guess what? This first box really doesn't make a difference. It's going to be all about the second box. Okay, no, 0 is okay. Because remember, a whole number, 0 works. Anything to the 0 power is 1. So 1 plus 15 is 16. Is that a polynomial? Yeah, it's a very simple polynomial, but it's not one. Okay, so if we can start at 0, what can we not use? Negatives, okay? And then somebody else back there talked about, who talked about rationals? Was it Angelica? Okay, so what's not going to work is any negative. So negative, not MEAG. negative, like, I don't know, let's keep it simple, -1, or any rational that cannot be simplified. That is a fraction where, even if it's simplified. So pick a simple fraction for me. Angelica, is your idea what you pick? A simple fraction. 3/6, which is a half. Okay. So I can simplify it, but even after I simplify it, I get a half. Because remember, what does x to the 1/2 power represent? That's another way to do it. I know it's been about a month. That's square root. Nice, Gage. Okay. So square root of x is not polynomial. So one of the ways you can kind of tell is if we start graphing these. And I'll put those back up there in a second. Okay. So if I take a look at x to the 1/2 power, I can see how it doesn't continue on to the left, so that is not a polynomial. If I use x to the -1, there's my vertical asymptote. Okay. All right. So we're done with this. So what should you do now? Save it and turn it in. So that's your ticket out the door for today. All you're going to do from this point is work on the practice.